we've obtained from the 03 run of the LIGO-Virgo collaboration. So the constraints on G mu coming from both the stochastic gravitational wave background and for the search from individual gravitational wave bursts, which can come from cusps and kinks. The second result, which I want to try and summarize, is assumes that there can be other contributions to dl by dt, so other decay channels, and that strings can decay not only into gravitational waves, but also into particles. So that's something that you might expect when the curvature of the string is of the order of the width of the string. And so that can happen, for example, at cusps and kinks. If the string can decay into particles and gravitational waves, then there'll be observable effects both on the stochastic gravitational wave background, and you can also expect a diffuse gamma ray background from these string networks. And then the third point which I'd like to try and consider is the possibility that after the string is formed, or after the phase transition that forms strings, there can be a subsequent phase transition which can lead to currents along the strings, so current carrying strings, as was first proposed by Witten. And as I think was also mentioned earlier, when strings carry a current, this can stabilize the loops, which stop collapsing. So they're stabilized by their angular momentum, and you can get a setup known as a Vorton, which may be stable on cosmological timescales. In fact, I'm going to assume it's exactly stable, so it can't decay at all. And then these Vortons can possibly act as dark matter. So one thing which I'll discuss is the constraints on models in which there are strings which then subsequently have currents along them, and what the constraints are for coming from dark matter. Okay, so why am I interested in Dlgt, and what's its role? Well, its role comes into determining the loop distribution, because it feeds directly into the loop distribution, which will be the central quantity to calculate these different observable effects. So as we've already heard, it's n of L t dl is the number of loops per unit volume with lengths between L and L plus dl at time t. And here I'm focusing only on the non-self-intersecting loops. So to determine the loop distribution, you have to solve a Boltzmann equation. And the Boltzmann equation is written here. So on the left-hand side, there are the various terms coming from taking into account the rate of change in time and the diffusion or the flux in L space. Here's the term in Dlgt, which I already mentioned, which can have different forms depending on the physical setup that you're looking at. A, of course, is the scale factor. And on the right-hand side is this loop production function, again, which has been mentioned, which is the rate at which these non-self-intersecting loops of length L are chopped off the infinite string network at time t and per unit volume. So given the dl by dt, with a clever change of variables, you can integrate this equation given a loop production function. And of course, the final step will then be to specify the loop production function, which will give you different distributions of loops. So as we've heard, string networks are thought to reach a scaling solution. And in all of this work, there's always people asking to enter the waiting room. It's a little annoying. Okay. So scaling solutions, I'm basically always going to assume that P of L of t has the form which is in the blue box. So there's a factor of t to the -5 from the scaling. And then there's a function f, which depends on the ratio of L over t. So of course, once you've specified the loop production function, once you've specified the physics of dl by dt, you can determine the loop distribution by solving this equation, and hence determine the different observational consequences. As we've heard, so in the previous talks, and I don't want to label the point anymore, the general picture that we have is that the loops are chopped off the network with time. So they, as the system evolves, they remove energy from the infinite strings. The loops decay into gravitational waves and possibly other forms of radiation. And that's responsible for the scaling solution of the infinite strings. So the infinite string network always has the same equation of state as the main background cosmological fluid. And the study of this approach to scaling and the properties of the scaling solutions have been attacked in numerical simulations. So both Nambu-Goto simulations, which we've heard about, and field theory simulations, which Mark has worked on a great deal. So as we've heard, they are generally limited in time, of course. But if you reach a scaling solution, then you can go beyond that limitation. At least if you don't remove the loops, of course, as we've just heard, if you remove the loops from the simulation, you can study the effects of gravitational radiation and back reaction. But in the big simulation itself, with the infinite strings and the loops, it's a little more complicated to do, let's say. And in Nambu-Goto simulations, particle emission, of course, is not included. So to combat some of these limitations, there's been a huge amount of work on analytical modeling, including by Tom Kibble initially and various other people. Okay, so I'm assuming, as I said, a scaling solution. We can determine the loop distribution, and regarding gravitational waves, as we've heard in all the talks before, there are two types of signals that we can search for at different frequencies. The first one is the stochastic gravitational wave background, which has been defined previously. So it's the energy in gravitational waves per logarithmic unit of logarithmic frequency divided by the critical energy density. And that's basically the sum of all the gravitational waves emitted by all the loops from when the network was formed until today. And for loops which are close enough to us, one can look also for sharp individual bursts, which would be the analog, if you want, of the chirp signal for binary black holes. This would be the analog from strings. So bursts which come from kinks, which we've heard about before. So it's when the string has a discontinuity on its tangent vector, which occurs as a result of intercommutation. So this emits a burst of gravitational waves. Kinks can also, well, they propagate along the string, so they can collide with each other. This also produces a burst of gravitational waves, which is isotropic in this case. And as we've also heard, there are cusps on the strings, basically at points which instantaneously go at the speed of light. And the waveform for each of these events, kinks, cusps, and kink collisions, can be straightforwardly calculated by solving the linearized Einstein equations in the wave zone approximation, so far from the loop. And here's the amplitude of the strain as a function of the length of the loop at a redshift z and observed frequency f. So as we've already heard, there's an amplitude term and a frequency dependence, where the frequency dependence goes as the power minus q, where the value of qi depends on whether you're looking at cusps or at kinks or at kink and collisions. And if you go from Fourier space to real space, the situation, the burst looks very much like this. So there's a sharp burst of gravitational waves, nothing like the chirp signal. But it looks a bit like glitches, which you can also have in the data, which can cause problems and difficulties anyway. So let's go to the constraints on cosmic strings, which were obtained using the third observing run from the LIGO-Virgo collaboration. So in this paper, so the assumption is that we're talking about purely local Nambu-Goto strings, as described by Barre-Zerouane. So gravitational wave emission is the dominant and unique decay mode as assumed in this paper. So L dot is minus gamma, a constant gamma times G mu, which I'll often write as gamma D, this combination, gamma G mu. Sorry, minus gamma D, there should be a minus here. So gamma is the power emitted in gravitational waves over G mu squared, it's dimensionless. And at least at high frequencies, it's dominated by the contribution from cusps, from kinks, and from kinking collisions. And each of these in itself is, well, you can determine it from the waveform, which I showed you on the previous slide, but it will depend on the number of cusps. In this case, here for the power emitted in kinks will depend on the number of kinks. And for the number of kink collisions, depends on the number of kink collisions on a loop, which itself is proportional to the number of kinks squared. So what we've done in this paper is we've assumed, or set, if you wish, that there's one cusp per oscillation period. And we've decided to leave nk, the number of kinks, as a free parameter, because it wasn't clear to us that this was something which was very well understood, whether it made sense to actually fix it to be 1 or not, as was done in the previous analysis, the 0102 analysis. So we left it as a free parameter, but let it range between values, take values between 1 and around 200. We put an upper limit of 200 because otherwise it would lead to values of gamma when you take the sum values of gamma, which would be larger than those seen in simulations. So we then searched for both burst signals and also determine the stochastic gravitational wave background in this O3 data. The expression for the stochastic gravitational wave background we've seen in a different form, but there's an analogous expression that you can write down, which comes from summing over the superposition of many bursts and removing infrequent bursts. So it's you can write this as a sum over the cusp kink and kink contributions, and it depends on the amplitude or the strain that we've already seen coming from each of those signals and the rate of events, of burst events, which itself depends on the loop distribution. And I should say that we've assumed standard lambda CDM cosmology. Okay, so then the next point is, what did we assume for the loop distribution? And what we assume for the loop distribution basically in itself goes back to what I said before. It depends on what we assume for the loop production function. So this was the expression I wrote down before. Here we've assumed gravitational radiation only. And the loop production function is, as I said, on the right-hand side. So what did we assume? So here, maybe I can just say very simply, we've taken the first model, which is labeled model A here, which is precisely the model or the result of the simulation that Jose Juan mentioned before. So in the radiation era, the loop production function here is scaling, as I said before, and it can be well approximated by a delta function. So all loops are produced with the same size alpha t at time t. And the values of alpha and of the constant c are determined from their simulations. And in that case, with this delta function, it's absolutely very straightforward to solve this equation. And I've written down here the distribution in the radiation era, where basically you can read off the value of c and the value of alpha from these quantities here. Now, the second model, which we've also looked at, is a model which is much more controversial. It's a model that was proposed by Larissa Lorenz and collaborators. And it's based on a different loop production function, one which was calculated by Polchinski, Rocker, and others in the early 2000s. And as you can see, it has a very different form to the first one. It produces loops on a whole range of scales. Here I should really have put a theta function cutting off the production at alpha t. But the curious thing, or the interesting thing, is that if you take this distribution and this loop production function and stick it in here, you can show that on large scales, it actually behaves in a very similar way to this one. Anyway, in this model of Lorenz, Rangel, and Sakilariadou, they take this loop production function, they solve the Boltzmann equation, and they calibrate the parameters c and chi onto the simulations of Rangel and company on large scales. Now, as Jose Juan mentioned, one has to make sure that there's conservation of energy. And the question of conservation of energy with this loop production function was already mentioned by Polchinski in his first paper, and the question is still open. I will not discuss that point further. I don't think I have anything new to say on that point, but let me just take this model and see what the constraints are from the O3 data. And then there's a further model that was analyzed, which is a model which in fact interpolates between these models A and B. And it's a purely phenomenological model, if you wish, and it aims to help understand the features to which the burst analysis and the stochastic searches are sensitive. So before I go on to the results, let me just sort of stress the differences between these models A and B. So as I said, they give very similar distributions on large scales. So on scales above, essentially here, gamma G mu. But they give very different distributions on smaller scales, where other physics, such as gravitation, radiation, and back reaction, may become important. And in particular, this model B has many, many smaller loops. And because it has many, many smaller loops, one would expect them to contribute to the stochastic gravitational wave background at high frequencies, and that's precisely what we'll see. So here are the results. So the top left panel is for model A, and it shows here we fixed G mu to be 10 to the minus 8, and we've taken the number of kinks to be 100. And it shows the contribution to the stochastic gravitational wave background from cusps in pink, from kinks in green, and from kink collisions in blue. And you can also see the O3 parallel integrated sensitivity curve. So the shape of this spectrum has been discussed by many people. I won't say anything more about it. Let me go to model B. As I said, model B has many, many more smaller loops. And indeed, as expected, it predicts a gravitational wave background, which is much higher, of much larger amplitude, for the same value of G mu and for the same number of kinks, which is 100. It also has two peaks, if you wish, relative to the one here. And these two peaks are because it has two characteristic scales. So the gamma G, which we saw here, this first characteristic scale, and a second characteristic scale here, which is thought to be associated, or is postulated to be associated to gravitational back reaction. The lower two panels shows the predictions for this hybrid model, C1. C1 is a model in which the loop production function is taken to be that of model B in the matter era, so lots and lots of small loops in the matter era, and of model A in the radiation era. So at high frequency, it basically reproduces model A, as you can see here for the kink case, it's the same amplitude. And for the matter era contribution is much more similar to model B. And the difference between these two curves is that the number of kinks here is 1 on the left-hand side. In fact, you can't even see the kink contribution. Where it's increased, the number of kinks is increased to 100 on the right-hand panel. Okay, that's the stochastic background. How about the burst search? So we looked for bursts in the data using a match filtered approach. So we used the burst waveform from cusps, kinks, and kink collisions. And the resulting candidates were filtered to retain only those which are detected in more than one detector within the time window, which accounts for the difference in the arrival time of the gravitational wave between the detectors. But as I said, these signals actually look very similar to glitches, which are in the data anyway. So you have to find a procedure to discriminate the true cosmic string signal from those glitches. And in fact, the conclusion of this analysis is that there are no events seen. There are some loud events, but in fact, they're well-known glitches. And so in fact, no gravitational wave bursts from strings were seen. Since the burst rate depends on the loop distribution and on the number of kinks, so here we fix the number of cusps V1, this non-observation gives constraints on the parameters. So here's maybe the summary of the results. So these are the exclusion plots, again for model A, for model B here, and for model C1, let me not mention model C2. So model A, again, is the model of Jose Juan. So the vertical axis is G mu. The horizontal axis, we varied the number of kinks from 1 to 200. And the excluded region is the region in pink. And you can see that if there's, for example, one kink, then the region essentially above 10 to the minus 8 is excluded. And as we've heard, this is already much less sensitive, if you want, to the well, it's negligible. I mean, this is much less important than the exclusion region coming from PTA. You don't see any excluded region from births and from model A, but in model B with all the small loops, there is an exclusion region from the non-observation of births. That's the quantity in the region in blue. And you also see that because there are so many small loops, the exclusion region for G mu coming from model B is much tighter, or it goes down to much smaller values of G mu of order 10 to the minus 14. I won't go on to models C1 and C2 because I'm a bit behind time, sorry. Maybe I can just summarize this by saying that relative to the O1 and O2 analysis where NK was equal to 1, the constraints on G mu are stronger by about 2 orders of magnitude for model A and about 1 order of magnitude for model B. Okay, let me go on to the second topic, which was to assume or to study what happens when there can be both gravitational radiation and particle radiation from loops. So this work is with Tanmay Vachaspati and Pierre Auclair, and it was based on the simulations by Tanmay and collaborators who carried out high resolution field theory simulations of abelian Higgs loops with kinks. So here you see on this plot the energy of a loop, and the loop itself is shown underneath. So the energy of the loop as a function of time. So the original loop had 4 kinks, and you see how the energy jumps when the kinks collide and emit particles. So the conclusion of their paper, what they propose in this paper, is that the energy lost by loops is probably given, or they suggest it's given by the standard gravitational wave decay mode, or the gravitational wave is the gravitational energy loss is the dominant decay mode for loops larger than a certain scale LK. That on the contrary, for small loops of length smaller than LK, particle radiation dominates, and it has a form which is given here, which they determined from their simulation. So I think you can understand that if you take the limit LK going to 0, this term goes away, and this would describe Nambu Goto strings. If you take the limit LK going to infinity, then particle radiation would dominate for all loops. So there's an extra scale in this problem, LK, and the question is, what is it? And they suggest that it's related to the width of the string, and with the constant beta here of order 1. Now, so the idea is to put this into the Boltzmann equation, which I showed at the beginning, and determine the loop distribution. Before showing you the answer, I just want to stress that because there's an extra scale in the problem, a length scale by itself, the loop distribution will not scale in the sense that I talked about before. There's another possibility that the loops, as we know, may have cusps, in which case they can also possibly lose energy through the annihilation of cusps. This would lead to an expression which has a slightly different form, power law form here, but the principle is the same. So basically, we can solve the Boltzmann equation for any form of dl by dt of which I've written here as minus gamma g mu times a function of L. The function j of L can be any one of these two, which you prefer to take. And you can solve that equation exactly. And I won't dwell into the details, but the answer is given here. And as you'd expect, what happens is that at late times, the distributions are very much cut off. The number of small loops decreases relative to the standard distribution. Oh yes, I should say we assume the delta function, the production function here. So the distribution is cut off for small loops. What's the effect of this cutoff of the distribution, either for kinks and cusps, on the stochastic gravitational wave background? You can see it here. Let's look at the case of cusps. The spectrum, when there was only gravitational wave radiation, was flat all the way to very high frequencies. it's now cut off and it decays above a certain frequency, which in fact you can calculate. So it decays above this frequency here, where LC and LK we've already seen. But it turns out that if you, for the values proposed, so LK and LC proportional to the width of the string, then these values are outside the bounds of future detectors, as you can see. These loops emit particles. Those particles can decay eventually into gamma rays. So we could also try and constrain the loops or the parameters gamma g mu through particle radiation or gamma rays. We calculated the contribution from strings to the diffuse gamma ray background. And so in the case of kinks and cusps, you can see the result here. The contribution from strings is at the bottom. And as you can see, it's well below the observed bound from Fermi-Lat. So there is no constraint at this point from the emission of these particles, which then decay into gamma rays. Okay, let me get on to the last topic very briefly, which is that of current carrying strings. So as we heard earlier, if other fields couple to the Higgs, which forms a string, then they can condense in the core of the string and propagate inside the string, leading to current carrying strings. And the simplest example of that would be a U1 cross U1 symmetry, where the first U1 would produce strings. It would be coupled to another further U1, which at a later time could be broken and lead to condensation of the fields here inside the core of the first string. And in fact, this is precisely the setup we tried to consider in this paper. So the setup we had was, as time evolves, there's a first phase transition which produces standard Nambu Goto strings. And then at a later time, T current, the second phase transition occurs, which produces currents which are on the strings that already exist. And therefore, from T current and onwards, there are current carrying strings. And the critical parameter in here will be the ratio between these two scales. So R, which is the ratio of the scale corresponding to the energy scale of the first phase transition to the energy scale of the second phase transition. Here, lambda is the Compton wavelength of the particle associated with the second symmetry breaking. So when the currents form, the charge will be a charge. You can estimate the charge conserved charge which will be trapped onto the string. It'll depend on the length of the string divided by the Compton wavelength of the charge carriers. And as I said right at the beginning, we're going to assume that this charge is exactly conserved from then onwards. There can't be any decay process for this conserved charge. And as a result of that, when the loop is formed with this conserved charge, it will radiate gravitational waves, lose length, until it stabilizes into a vorton. So a circular loop, which is whose collapse is well, I mean, it can't collapse because it's of angular momentum. So we wanted to study the number of vortons which are formed as a function of time. And so to do so, we wanted to determine the loop distribution. So now it's the number of loops per unit volume of length L at time t and with charge n. And to do that, we want to use a similar Boltzmann equation to before, except for now that we have to add a bit of more input. Firstly, that the charge n is conserved on a loop. And secondly, that the loop will radiate, or its length will change, provided its length is larger than the size of a vorton. So this is what this theta function is saying here, saying that if the length is larger than the size L0 of n, the loop will radiate gravitational waves until it gets to L0 of n, the size of a vorton, and it will stay as a fixed circular vorton configuration. So in other words,
you have approximately 3 minutes left.
Yes. So in other words, we wanted to solve this equation. We've assumed an initial Vashus-Barty-Vilenkin distribution. at time t initial. We've assumed delta function, loop production function in this epoch between formation and when the second phase transition occurs. And then we've again got this delta function, loop production function, but with an extra term for the charge in the resulting period. I'll go on, I'll skip these details, but maybe I can just say that we determined the number of photons formed from the initial conditions at the initial first phase transition, and for the first time from the loops chopped off the infinite string network. And from there, we could determine the density parameter of relic photons. So basically, the number of photons, the energy density in photons divided by the critical energy density of the universe. Those photons appears on cosmological scales as point particles, and we assume that they're going to behave as dark matter. And therefore, we can calculate the relic abundance of all photons. So the x-axis here is 1 over the curly r, which I introduced before. The y-axis is g mu. And here you can see the photon abundance, which varies from crazy values from about 10 to the 25 to 10 to the minus 39. And the green line is the region with which is basically of order 0.3. So all the region to the right of this green line is excluded. So basically you can put constraints on the parameter space g mu and 1 over r. I'll skip that and go to the conclusion since I'm running out of time. So in this talk, I've tried to present the latest LIGO-Virgo O3 constraints on Nambu-Goto strings, where we've now taken nk as a new parameter, and we've taken 3 different models. I also discussed Nambu-Goto strings, cosmic strings, beyond the Nambu-Goto picture, trying to include the effects of double particle emission and currents. I wanted to mention some effects of modifying the cosmological background, but I don't have time, so I'll refer you to this. I mean, there are many people who've worked on it, but I think this is a very nice paper on the subject. And to lead on to the next talk, I think there are very interesting open questions. Jose has already talked about gravitational back reaction and also primordial black hole formation from loop collapse and cusps is a very interesting question, which I think the next speaker will talk about. So I'll stop there. Thank you.
Okay, thank you very much for the very nice talk and for speaking to time. So there's a question by Yoon Jiang. Can the speaker, can the person please unmute and ask the question?
Sorry?
So there's a question by Yoon Jiang. I'm just wondering if Yoon can just unmute and ask the question. Okay, I can ask the question on his behalf. So the question is, are cusp collision and Kink collision possible on loops? If yes, why ignoring these contributions in calculating the gravitational power spectrum? Are they negligibly small?
So a cusp is something that forms at an instant in time. So I think the probability of a Kink collision is basically negligible. So yes, we didn't consider it.
Okay.
Sorry, to answer the question directly.
Yeah, probably to answer the question. The person is not here today. Okay, so there are questions by Mark Hindmarsh. Mark, can you just unmute and ask?
Thank you. Yes, thanks, Stanley, for a nice, clear talk. So I guess I'm going to ask the same questions I asked Kai. I mean, if you were to accept that most strings sort of collapse immediately into particles, but there may be, of course, some small fraction which behave like these very special loops that Tanmay and his collaborators ingeniously constructed. What would the differences be in your sort of conclusions?
So I suspect, of course, that the gravitational wave background would be much reduced, probably be negligible. For particle production, I suspect that I think you know the answer better than me, right? I suspect that the gamma ray background will be rather larger, but to what degree it's not clear to me. But I think you've worked on that yourself.
Yes, just in the scenario where everything goes into particles, but I haven't really thought about these sort of mixed scenarios where there's
right. So I think that I think more work needs to be done on this mixed scenarios. My impression.
Okay. Thank you.
Sorry, I can't give you a better answer without doing it.
Okay, there's a next question by Marek. Marek, can you just unmute and ask?
Thanks. So I actually had a question. In the very first part of the talk, you had a couple of distributions or loop production functions. So the second one by Mary and Rajeval, sorry, Rajeval. But in the second part, if you included particle emission from that loop production function, wouldn't it change the results completely? Do I understand correctly that it will, well, essentially kill the extra production you had from the tiny loops?
So that's an interesting question. It's something we want to do, is to try and include the effect of particle production with that that loop production function. Absolutely. It's something that we're doing at the moment.
Thanks.
Okay, correct. So there's still time. So this question by Honish. Can you just unmute and ask?
I have just a small curiosity. So, I mean, this is a curiosity directed both towards the speaker and also to you, Ranjan. So, when you talk about cosmic strings radiating particles, especially in the context of photon, you showed us that can be give us some constraints. So, why not neutrino? Why? I mean, can we? So, is it possible to look at the neutrino spectrum that the cosmic strings emit, and possibility to constrain using the neutrino detectors and telescope that we have today, or is it really small and the efficiency in the stats actually small?
So I'm sure that somebody else can answer that better than me, if somebody else wants to take that question. It's not something we've calculated, but possibly it's an interesting thing to do. Yeah, maybe we can discuss that in the discussion session.
And my expectation would be that the neutrino constraints would be much weaker than the gamma ray constraints.
Yeah, if the neutrino and the gamma ray emission are of similar quantities, I do not know that. If they are of similar quantities, then obviously the gamma ray constraints will be much stronger.
Yes.
Just because the neutrino cross sections are weak. That's it.
Yep.
Okay, we still have time for one more question by Kai. Kai, can you please unmute?
Yes, yeah. Thank you very much for this very interesting talk. I have a question on the scenario of the current carrying strings that you mentioned. Yep. I think you gave an estimate of the entire charge or current that accumulates on the string in terms of the width and the wavelength of the charge carriers. But you also mentioned the timescale T current, right, that distinguishes between the two regimes. I was wondering what sets that timescale? When you actually see the transition.
So maybe I didn't specify the picture very well. So the assumption is that there's a first phase transition that produces the strings. Mm-hmm. And then there's a second phase transition at a later time. And it's thanks to that second phase transition that the currents are formed. So that this is if you want, is a free parameter. It's related to this ratio R. Mm-hmm. So it's a free parameter in our model.
Now, that is a phase transition in the vacuum structure on the cosmic string itself?
Well, if you want, probably the easiest way to think about it is in the case of the U1 cross U1. Mm-hmm. I don't know if that helps. If you couple the fields in the right way, you can have the second field will condense in the core of the first field, mm-hmm. of the string, sorry. What I did want to say is I think you were asked this question, or somebody asked this question of, in fact, in principle, the tension and the energy per unit length of these strings are different once they have a current on them. But in this regime in which R is much larger than 1, in fact, they're basically identical, which is why, if you noticed, I only ever talked about the energy per unit length. And the tension is, to all extents and purposes, the same as long as this ratio of these two scales is large.
I see. Okay, thank you. So then you have additional parameters in the underlying particle physics model that control the time of the phase transition. At this level here, it's basically a free parameter, and you can choose the parameter such that the phase transition occurs at a specific time. This is when you go from one regime.
Right, and your constraints will depend on this ratio, right? So in principle, you can't believe this analysis very close to this line, because as I said, we've taken R to be much larger than 1. Mm-hmm. Okay, but as you can see, the constraints are quite strong, right?
All right, good, thank you.
Okay, all right, thank you very much for this discussion on the talk. So let's move on to the next speaker, Alexander Jenkins. Alex, can you please share your screen?
Yeah, sure. Can you hear me okay?
Yes, yes, I can hear you. Okay. And I can see your mouse on this. Okay, all right. So you have 20 minutes. Let's
Brilliant. Thanks very much.
Thank you very much.
Thanks. Yeah. So for those who don't know me, I'm Alex. I'm a PhD student just finishing up at King's College London. Yeah, wanted to say a big thanks to the organizers for inviting me to this great workshop. It's a pleasure to be giving a talk. I'm going to tell you about a paper which came out earlier this year to do with nonlinear gravitational wave memory from cusps and kinks on cosmic strings. This is work with my supervisor, Mary, and it's recently been accepted in CQG. So the plan for the talk is I'm going to start by talking about what gravitational wave memory is and why I think it's interesting and worth thinking about. Then I'm going to talk about cosmic strings, but basically everything in this section has already been covered by the other great talks. And then finally, I'm going to talk about calculating the nonlinear memory generated by these cusps and kinks on cosmic strings. So the gravitational wave memory effect, at least in its linear form, and I'll explain what that means in a second, this has been known about since 1970s. It's a very well understood phenomenon where essentially for particular kinds of gravitational wave sources, you can end up with a permanent offset in the gravitational wave strain signal. And this is associated with sources where basically you have a blob of matter that goes off to infinity. So for example, if you have some kind of unbound orbit where two objects scatter and go to infinity, or if you have something like a supernova, so it explodes and sends stuff away, typically the gravitational wave signal you see from these systems ends up with this permanent kind of offset. So it wasn't until much later in the 1990s that people realized that actually you don't need to have these special kinds of systems. There's actually a memory effect like this that occurs generically for basically any source of gravitational waves. And this is called the nonlinear memory effect in contrast with the linear memory effect. So with the linear one, you get this permanent offset just by essentially solving the linearized Einstein equation for that source. In this case, this is really a nonlinear ramification of GR. So this was first discovered by Christodoulou in 1991 using some quite sort of formal relativistic techniques. But there's this nice kind of intuitive explanation due to Kip Thorne that you can think about the gravitons are emitted by a gravitational wave source as individual, bits of stuff that get sent off to infinity. The gravitational waves themselves carry energy and momentum. And as such, you can think of them sourcing linear memory as well as they propagate to infinity. And so if you kind of add up all of these linear memory contributions from the gravitational waves that are emitted, then you reproduce exactly Christodoulou's formula. So this is a nonlinear effect because it's gravitational wave energy itself generating further gravitational wave contributions. And I'm showing here a nice figure by Mark Favata showing this effect for a binary black hole signal. So obviously this is a bound system where you've got two black holes spiraling in and merging. So you've not got stuff that's getting sent off to infinity other than the gravitational waves. And you can see this kind of permanent offset building up over time. Okay, so why is this an interesting thing to think about? I think the key argument here is this is a prediction of GR in the nonlinear and dynamical regime, which is really where we want to be studying GR to see if we understand how gravity works in the universe. We know that this is observable with gravitational wave observatories. So this is great. We have these instruments that can go out and search for this really interesting effect. And there's also this whole body of work, I think particularly by Strominger and collaborators looking at ways in which the memory effect is linked to other properties of essentially gravity at low energies. So it's linked to the kind of global structure of space-time in terms of the BMS symmetry group of asymptotically flat spacetimes. And it's also linked to the soft theorems which govern the kind of low energy scattering processes in a quantum theory of gravity. So I think there's a lot of motivation to study this memory effect and try to test it with this range of gravitational wave experiments that we have. So in terms of existing work on this in the literature, almost everything is focused on binary black holes. This makes sense because we know they exist and we know that they're copious kind of sources of gravitational waves. So in particular, the nonlinear memory signal associated with supermassive binary black hole mergers is a really promising target for pulsar timing arrays. So I direct you to this recent paper by the Nanograv collaboration who are saying upper limits on this. Basically, if you had a sufficiently massive and sufficiently nearby system like this, then we should be able to see this memory signal with pulsar timing arrays. It should also be detectable by sort of future upgraded versions of LIGO and Virgo, but only by combining statistical evidence in favor of this memory signal being present over sort of thousands of different events. So it's quite hard to see it individually on an event by event basis, at least for these particular systems. So that's all to do with binary black holes. Obviously, you know, the whole point of this workshop is to think about stuff beyond what we already know about. And so I think it's interesting to think about other gravitational wave sources and the nonlinear memory effects that they could give rise to as well. So I mentioned before that, you know, kind of gravitational scattering, supernovae, also gamma ray bursts, these are all really good sources of linear memory. But in terms of sources of nonlinear gravitational wave memory, there's really not very much out there in the literature that's not to do with binary black holes. So I wanted to highlight this nice recent paper by a group at King's, which is led by Yosu Arakoechea. They were looking at collapsing circular cosmic string loops, so a kind of idealized setup where it's perfectly circular and it just contracts. And they were looking at the combined linear and nonlinear memory emitted by these loops. There's a linear memory contribution because you get matter that's radiated off to infinity, but you also get nonlinear memory from the gravitational waves that are emitted. So that's one example. But I'm going to go on and talk about, you know, so these circular loops are not usually what we think about in terms of gravitational wave emission from cosmic strings. We usually think about cusps and kinks. And so we've tried to calculate the memory signal associated with that, which I'll talk about in a bit. Okay, so that's gravitational wave memory. I'm now going to talk a little bit about cosmic strings, but I'll be very brief because the other speakers have already covered all of this. So essentially, cosmic strings are one-dimensional topological defects, which may have been formed in the early universe. They're generic. You know, we expect these things to be formed by very many theories beyond the standard model. And typically what happens when you form these things is you get one or so long string per horizon. That's the black things in this simulation box here. And these things wiggle around, and if they kind of curve over and intersect themselves, they can chop off loops. And so you fill up your Hubble patch with many, many small cosmic string loops, which are the red things in this box. And these things are then massive objects which wiggle around at relativistic speeds. And so they generate a lot of gravitational wave energy, and the loops then decay. So when we think about these cosmic string loops and how they evolve, there's two kind of key approximations or assumptions that we usually use. The first is the Nambu Goto approximation. People have already talked about this. I think Mark Hindmarsh has mentioned in a couple of questions about, you know, alternatives to this if you were to do field theory simulations. I'm not going to comment on that really. Everything that we've done in this paper is in the Nambu Goto approximation. And essentially this assumes that the width of the cosmic string, so it's a kind of subatomic length scale, is much, much smaller than the size of the loops, which is an astronomical length scale. And in the Nambu Goto approximation, you essentially take the string width to 0. So assuming your strings don't have any kind of non-gravitational long-range interactions, this means you can describe their dynamics with just a single parameter, which is the string tension G mu. And this has already been talked about. There's another key assumption, which I think has kind of been hinted at previous talks, but has been less maybe explicitly talked about, which is the assumption of linearized gravity. So we assume from the start, typically, that the loops live in a flat background spacetime, and that any corrections to this due to the loop can be treated as just linearized gravitational waves that are generated by the motion of the loop. And the sort of rationale for this is that, you know, G mu is a very small number. It has to be consistent with observations. And so we expect any kind of gravitational effects of the loop to be suppressed by these pairs of G mu. So that's the kind of rationale for doing everything in linearized gravity. So if you take these two assumptions, you play around with the equations, you find that the main ways that you can emit gravitational waves from these loops, you can characterize them in these three kind of emission modes. So you get cusps, which are points on the loop, which instantaneously move at the speed of light, and they emit a really kind of strong beam of radiation in this really narrow kind of range of directions. And this has a characteristic power law frequency profile in the gravitational wave strain. You get kinks, which are discontinuities in the tangent vector of the loop, and these propagate around the loop at the speed of light. beaming out gravitational waves like a lighthouse as they go. And you can also have kink collisions, which Dani was mentioning in her talk as well. This is where you get two kinks traveling in opposite directions around the loop, and they collide and they emit an isotropic burst of gravitational waves. So because it's isotropic, this is actually less interesting from the point of view of the memory effect. The reason being that you need to look at the kind of emission pattern of the gravitational wave energy and take the transverse traceless component of that to get the memory gravitational waves. And if you've got this kind of isotropic distribution, that transverse traceless part vanishes. So there's no memory associated with kink collisions. But cusps and kinks, on the other hand, because they're so tightly beamed, they do have a non-zero TT component, and so they will give rise to memory effects as well. Okay, so I'm gonna get to the punchline now and talk about nonlinear memory emitted by these cusps and kinks. So I've sort of motivated why we want to think about this, just in terms of, memory is interesting and everything is focused on binary black holes so far. We want to think more generally about what kinds of gravitational wave memory signatures we could go looking for in the universe. We know that cosmic strings are a really promising source of gravitational waves across the gravitational wave frequency spectrum. So there are, it's interesting to think about what the kind of gravitational wave phenomenology of these objects is. But there's two, so points 3 and 4 here, these are two particular reasons that cosmic strings can be interesting in terms of their memory effects. One is that the memory tends to push things to lower frequencies. So to understand why this is, think of the example of a binary black hole. It evolves over many, many cycles until it eventually merges. And the memory effect is associated with the total timescale of the signal, right, which is much longer than the period of the gravitational waves. And so that means that because it's a longer timescale, it's a lower frequency, right? So if you imagine seeing a kind of massive binary black hole signal in the LIGO-Virgo band, the memory pushes that to lower frequencies and it makes it harder to actually observe. So what helps us here is that cosmic strings, they don't have that kind of separation between the total time of the signal and the period of the oscillation, because it's a kind of burst-like thing where you just have a few cycles. And also there's a strong component at high frequencies. So even if things do get dragged to lower frequencies, you can still hope that there'll be a strong effect at kind of observable frequencies. The other reason that it's interesting to think about this, I think, is that, so there's, in principle, there's no reason that the angular pattern of the memory gravitational waves are emitted. There's no reason for that to be the same as the emission pattern of the primary gravitational waves. So because we know that cusps and kinks emit into these really narrow beams, which means only a small fraction of them are observable, in principle, the memory could leak out of this beam. You could have a different emission pattern, which could help you, see these things more easily. So we've done this calculation, and indeed, this is what we find. So you can see here this is the emission pattern on the sphere for different contributions to the gravitational wave energy. So in blue, I've got the kind of primary cusp signal, the kind of standard Nambu Goto result that people use. And you can see, as I was saying, it's channeled into this very narrow beam. In fact, the size of the beam here is greatly exaggerated to make it visible. In purple, I've got the first order memory effect. So, pardon me, the nonlinear memory. And you can see that although this is still kind of concentrated around the northern hemisphere of this sphere, it is much broader. So you can, in principle, see the memory effect even if you're outside of the beam of the cusp. In red is what I call the higher order memory, which I'm going to come back to on the next slide. So this is what things look like in terms of kind of distribution on the sphere. Thinking about what the actual signal looks like in the time domain. So this is a plot here of the gravitational wave strain as a function of time. The blue line here is the standard cusp signal. So you can see it's kind of very sharp around the time at which the cusp forms. The red dashed line is the memory effect that we calculate. So this looks very different. In fact, if you look at the kind of Fourier transform of this waveform, you find it has the same frequency scaling as the original waveform, which is interesting. It's just that the different frequencies have different kind of phases, such that if you look at it in the time domain, it looks very different. So I wanted to point out, so when the blue line gets very sharp here around time 0, you can see that the red dashed line, although originally it's kind of gradually ramping up, near time zero, it very sharply increases and then it kind of levels off again to give you this permanent memory offset. And if you were in the right kind of location, so, you know, somewhere in this beam and you could see both of these things together, you would see this red solid line. So you would see the original signal kind of tilted by adding the memory contribution. Although I should say I'm exaggerating the size of the memory effect here to make it visible. So yeah. Okay, so I had a brief mention on the previous slide to what I call higher order memory. So the idea here is, you know, we took the primary cusp gravitational wave signal, irradiates this energy to infinity. This causes a memory effect through GR, right? But then the memory effect is also gravitational waves propagating to infinity. So in principle, this generates a second order memory effect as well. And in fact, because the waveforms we're working with are so simple, they're just power laws in frequency, you can actually do this calculation. You can turn the crank and keep going and actually get all of the corrections to all orders. Beyond the second order, there's a kind of pleasing pattern which emerges. So yeah, so you can think of these added contributions as the memory of the memory, and then the memory of the memory of the memory, etc. And in principle, you know, if you had an exact GR solution to the gravitational waves being generated by this, you need to include all of these contributions, although there will be other nonlinear contributions which aren't included here. Okay, so the interesting result, and the thing that we were really surprised by, was that if you look at large enough loops, this kind of sum of adding up all of these contributions to the memory actually diverges. So you can see here, I'm plotting on the vertical axis the total energy radiated in gravitational waves as a fraction of the energy of the loop. So this is for a single cusp. So really you want this to be much smaller than 1, right? Because you want the loop to lose a small fraction of its energy through the cusp. And in the sort of the leading order approximation where you don't include any memory effects, you can see this is just basically equal to G mu times some numerical factor. So it's very small. You can see that, and on the horizontal axis, I have the length of the loop in meters. And you can see that, you know, for small loops, everything is fine. These contributions get smaller and smaller, and they're really tiny once you go beyond the first couple of orders in the memory. But there's this kind of critical length scale above which things start to diverge very quickly. So obviously, you know, things don't diverge in the universe. Obviously, there's some kind of breakdown here in terms of the assumptions that we started with. And it's tempting to take away from this that we shouldn't be treating the gravitational wave emission from this cusp in terms of linearized GR, right? Because clearly things here are getting very nonlinear. So the kind of conclusion from this is that we shouldn't be treating cusps in this kind of weak field gravitational prescription. Okay, so how can we fix this, right? Because this is clearly... Okay, thank you. Yeah, I'm getting towards the end now. So how can we fix this? So Jose Juan and a couple of others in their slides have talked about back reaction. In principle, this could help you, right? Because we expect back reaction to smooth out sharp features on a loop. So I'm showing a nice figure from an old paper by Kwasniok and Spergel who studied this. And in principle, if you smooth out the cusp, you reduce the high frequency gravitational wave emission, and you can reduce the associated memory effects. I think it's hard to say anything definitive here, especially because I think most kind of back reaction studies are themselves based on a kind of linearized prescription. But typically the timescale that people find for this sort of evolution is very long. So it happens over many oscillations of the loop, right? Whereas really, if we want to smooth off the cusp and prevent this divergence, we need it to happen on a very short timescale, much less than a single loop oscillation time. So it's quite hard to see how this could fix things, but you know, obviously you need to do a full GR calculation to see what happens. Another possible explanation, which is a bit sort of tentative, but might work, is if you were to form a horizon which could trap some of this energy and stop it being radiated to infinity. And in fact, so Mary and I had this previous paper where we had suggested, based on a kind of heuristic hoop conjecture argument, that you might form such a horizon at a cusp if the cusp was sufficiently on a sufficiently large loop. In fact, it turns out that the range of loop lengths for which we predicted this to occur, just based on these very simple arguments, is exactly the same as the range of loop lengths for which the memory effect diverges. And if you take into account this process and take into account how it should reduce the high frequency gravitational wave emission, you find that actually all of the memory contributions converge very nicely. So this seems like it might be one possible answer to this problem of how we deal with this divergence, but futures, we need to study this really in a kind of full general relativistic setup. So I'm running out of time. I'm just going to wrap up very quickly. So memory, this has all been about cusps so far. The story with kinks is much more boring. Basically, everything converges very nicely. This is to do with basically the fact that kinks are long-lived rather than transient things like cusps, and you get interference effects between different points in its history, and so everything kind of cancels out. This kind of agrees with the thinking about this black hole formation story, because that's not predicted to happen for kinks. So it sort of makes sense that also the memory should be convergent here. And then the final slide, and I promise I'm done, is about observational implications. So when we started this study, we were thinking, oh, maybe this extra memory contribution could help in terms of detecting the stochastic background from cosmic strings. Obviously, in order to compute any observables, you need to have a convergent answer. So you need to assume some way of resolving this divergence with the cusps. If you assume that this black hole story is correct, then you find that the memory contributions are really, really tiny, and it's basically impossible to see them. But in principle, there could be other ways of resolving this that would allow the memory effect to be much larger, and that could give more interesting answers for this. Okay, so to wrap up, I hope I've convinced you nonlinear gravitational wave memory is interesting and it's worth studying for sources beyond just binary black holes. Our key result of our study into memory from cusps and kinks is that the memory from cusps diverges if you use the standard waveform, so the standard assumptions about linearized gravity. And it seems as though we need some kind of unknown strong gravity physics to fix this, right? And the linearized prescription is sort of breaking down here. We've argued that black hole formation might be one possible resolution, but really we need to go to numerical relativity or something like that to see what happens. Okay, that's it. Thank you very much for listening. Oops.
Okay. Thank you very much for this very nice talk. Are there any questions? If you can unmute and ask, raise your hand. Yeah, Jose, can you please unmute and ask?
Hi, Alex. How are you? So I have a comment and a question. So first, the comment. So the cure that you propose to have, which is the formation of a black hole. So we studied with Ken Olin and Alex Valenki this idea, and so we concluded that this doesn't work because in order to use the Hooke conjecture, you have to go to you have to take into account the energy, but not the kinetic energy. As you know, the cusp is something that is moving something very fast. So if you take into account that energy into the Hooke conjecture, of course, you may say you form a black hole. But that's like saying, I take a ball, I boost it, therefore it has a huge energy, and therefore it's going to produce a black hole. So in that case, we know what to do. The thing to do is to go to the red frame, and then you see the ball. There's no problem. So here, you can do something similar. You can go to a frame in which you get rid of all this extra kinetic energy, and then you see that the black hole does not form by the Hooke conjecture. Okay? That's the comment. The question is, I am a little bit intrigued about the whole calculation because you seem to be saying that when you do the calculation of the linearized radiation, there is nothing sick, there is nothing wrong. The total energy emitted by the cusp is finite. But nevertheless, when you do this other calculation of the nonlinear memory, you see something that is sick. So my question is, should we now go to do the same calculation for every source, or you have some insight of why or what went wrong here?
Yeah, so thanks very much for the question. Maybe just to reply to the first comment, I think it's very tricky because, of course, the Hooke conjecture is this, it's not a theorem, it's this kind of heuristic tool for thinking about black hole formation. I think that, the fact that this range of loop lengths for which this divergence occurs matches exactly just this very heuristic idea is some kind of indication that maybe we're on the right track. But I think ultimately we need full, numerical relativity simulations or something along those lines to figure out exactly what's going on. In terms of your second question of, trying to have some intuition of what's going on here, I think one way that I think about it is, so if you just take the basic cusp waveform, if you think about the total energy radiated as a function of direction on the sphere, if you look in the center of the beam, then actually the total energy radiated in that direction diverges. It's just that because it's a very thin beam, it's kind of hidden.
Total energy.
Sorry?
The total energy is finite. You mean
the total energy once you integrate over the sphere, because the beam gets very narrow, right? But then if you go to the first order memory effect and you calculate the total energy radiated, then it diverges. You need to have, so there's a lot of technical details I didn't want to include, but essentially if you calculate it's to do with the fact that this kind of divergence in the center of the beam kind of leaks out into other directions through the kind of nonlinear nature of GR. And so if you calculate the total energy radiated by the leading order memory, this diverges unless if you put in a cutoff at the string width scale, delta, right? But if you do this, then you become sensitive to this very, high energy scale, and this propagates into higher order corrections. So you get powers of essentially L over delta, right, with some powers of G mu as well. And so, of course, L is much larger than delta, and things get very large very quickly. There's another just quick slide I can mention as well for getting intuition about this. We played around with a kind of toy model if you have a waveform which is just a Gaussian pulse, and you can change how kind of sharp this is by just changing like the standard deviation, if you like. And we found that you can replicate this kind of divergence with this very simple model in the case where this quantity, so H dot, where the maximum value of that is much, much greater than 1, then you get this divergence. And this corresponds to having a energy radiation of essentially more than 1 Planck mass per Planck time. So it's this kind of super Planckian radiation. This is one way of thinking about it. And this is a way of understanding why you don't get things like this for example, for binary black holes, because in this case, this quantity is bounded by a number which is basically of order 1. So you can never have this very large kind of energy radiation rate. So yeah, I don't know if that helps at all.
Well, that helps a little bit, but in this case, I kind of understand it because it's trans-Planckian. But in the case of the cusp, I can regularize the cusp by introducing, let's say, some tiny wiggles or some current that allows me to go to a finite Lorentz factor, not an infinite Lorentz factor. So everything is fine, and the amount of total energy is basically the same. If I look from far away, I see the same beam. The difference is that the core is smooth. Would that also create a problem?
But at what scale are you smoothing it though? Because you would need to, based on what we've calculated, you'd need to smooth it on a scale much, much larger than the scale of the string width.
Yeah, let's do that. I can smooth it at the scale like 10 times the scale of or 100 times, doesn't matter. I can introduce some current that is smooth it to the Lorentz factor that I want.
Right, but so then you're introducing some extra physics in order to fix the problem. So our claim is in the standard picture with Nambu Goto strings, with linearized gravity, then things break down.
I'm not saying that this is the solution to your problem. I'm saying that once you take that source, if you want, a regularized source, this looks to me almost exactly the same as the real source from far away. Now, do I have to do now the calculation for that other source that I just invented to see if there is a nonlinear effect as well? Because to me, once you regularize it, there is nothing sick with the linearized calculation. Therefore, there is no intuition or any red flags that tells me, okay, you have to be careful to do something nonlinear might be going on. I don't see it here.
Well, for me, the red flag is if you do this regularization, so if you do this cutoff at the string width scale, then the observables are sensitive to that cutoff in a way that blows up when you go to higher orders. This is what we find in the calculation.
Right. It isn't the
Sorry, if I may, I think we're already over time. So maybe we can discuss this in the discussion session.
Yeah, maybe we can follow up on this later.
Yes. All right. Anyways, thank you very much, Alex, for this very nice talk.
Thank you.
Yeah. So we will move on to the next speaker, which is Professor Sachiko Yanagi. Can you please share your screen?
Yes. Do you see the slider?
Yes, I see the slides. Can you just please do a full screen?
Yeah. Okay.
Yes, I can see it. Okay, all right. Okay, yeah, please start here.
Okay.
Thank you.
So first of all, thank you for the organizers for giving me this opportunity, nice opportunity. to present my work. I'm going to talk more observational aspect of cosmic string. And this work is done in collaboration with Parkes Pulsar Timing Array team in Australia. We analyzed the pulsar timing array data to look for gravitational wave burst from cosmic string. So let me start with the introduction. So as it's clear from other talks of that session, cosmic strings are very important object because it can be a unique way to access the early universe physics. And gravitational wave is a powerful observational tool to prove cosmic strings. And in this talk, I will focus on pulsar timing array to look for gravitational wave, and especially for single gravitational burst event. Because in most of cases, people talk about the stochastic gravitational wave background because gravitational wave from cosmic strings are numerous, and typically they overlap one another, and you cannot distinguish as a single burst. But if we are lucky and if there is a nearby event, let's say inside our galaxy, then it may be possible to identify one burst event. So we looked such event in pulsar timing array data. So let me start with what type of gravitational wave we are looking for. This was also mentioned in the previous talks, but let me describe again. So cosmic string loops emit strong gravitational burst from cusp, singular point cusp. And the amplitude of gravitational wave is given in this form in Fourier space. So it's proportional to the tension of cosmic string, and of course inversely proportional to the distance to the source. If you look the waveform in time domain, it looks like a spike. And the amplitude of this spike is proportional to tension and inversely proportional to distance. And the width of the gravitational wave event is proportional to loop size. And the sharpness can change depending on the observation angle. So this type of signal we want to look. And let me talk a bit about observation. So Parkes pulsar timing array observe 20 pulsars, 1 hour for each every 2 weeks. And somehow, let me use a PDF. Do you see my PDF slide?
Yes, I can see it now. Yes.
Yeah, sorry, somehow Keynote finished. It's in full screen now, right?
Yes.
Okay. Yeah. So this is what you observe. So you see the pulse from the from one pulsar for each beam, but it's not very clear. It's very noisy. So what they typically do is this folding process. So basically, you sum up all the beams so that the signal is accumulated and you find a strong peak, while noise doesn't have correlation. So the noise gets suppressed. So in this way, you can take out the signal, and you do the same after 2 weeks. And if there is any mechanism to change the pulse arriving rate, pulse arriving time, then you find the position of the peak is shifted. And this difference of of this time difference is what is so-called timing residual, and this is observable in pulsar timing array. So if this timing residual is induced by gravitational waves, the timing residual is given by the time integral of gravitational wave amplitude. And of course, it depends on the antenna pattern. But let me skip about this antenna pattern thing. It just depends on the position of the pulsars and the position of gravitational wave source. So if we have this gravitational wave signal from cosmic string, then it looks like this in terms of timing residual. So it's no longer spiky. And there is another effect we have to take into account, which is so-called post-fit effect. The thing is that we don't know the true pulsar period. So if we assume long pulse period, then we get non-zero timing residual, even without gravitational wave signal. And it has this linear trend of the timing residual signal. So to correct this, you have to correct the time, you have to change the pulse period and to remove the linear trend. In this way, you can remove this fake value of timing residual. But if you do it for data with signal of gravitational wave, then it also affects the gravitational signal, the gravitational wave signal. So if you make this post-fit to the signal of cosmic string gravitational wave, then after the post-fit, this looks like the shape changed. So this is the shape we want to look in the timing residual. So this is simulated timing residual. We injected the gravitational waveform from cosmic string by changing the width of the event. And this is what you should observe in pulsar timing data. And there is two parameters. One is width of the gravitational wave event, and the other parameter is epoch of the gravitational wave event. We define it at the position of the peak. So what we did is as the following. So now we can predict how timing residual looks. So we prepare a lot of templates and compare it with data, pulsar timing data. And we basically look signals which looks like, which has a similar shape with template, but at the same time, we also check the quadratic pattern, quadratic moment pattern. And here we define the detection statics in terms of amplitude of the event and also covariance matrix, which has information of the pulsar noise. And this is the search result. This figure has a lot of information, so let me explain one by one. And so here we show the detection statistics in terms of the duration of the burst event, so width of the event, since we have two parameters, width and epoch. So we changed these two parameters and plot in one figure. And as you can see, there is an interesting event here where we find quite high detection statistics. And in this map, we show the position of location of the gravitational wave source. And this cross point is location of pulsars. So although we found high detection statistics, we don't know if it's likely or not. We cannot claim the detection by just looking at the number. So we made a simulation to test how likely is it as a cosmic string event. So this is the simulation we made without gravitational wave injection. It's just composed by noise of pulsars. And we test 100 realization and plotted the detection histogram of detection statistics. And as you can see, even without gravitational wave injection, we found event like detection statistics is like 17, 18. So it's possible that we get this high value of detection statistics. And coming back to the same figure, we plotted this dotted line, which shows the false alarm probability is 1%. This is obtained from our simulation. So it means that the curves below this dotted line is normal. It could happen even without the gravitational wave signal. But we still see the event which has a higher detection statistics. So let us investigate these three curves. So for this blue and light blue event, we found that only one pulsar is making the detection statistics high, which is this pulsar. So if you look at the post-fit residual of this pulsar, you find this jump here, which looks quite similar to the cosmic string signal. And this is apparently cause the high detection statistics. But this pulsar is famous for having a poor red noise modeling. And also, since this pulsar is kind of isolated, there is no other pulsars to compare and confirm. Maybe in future international international pulsar timing array could help, but only with PAX pulsar timing array, we couldn't check further if this event is real or not. So we basically removed this pulsar from the analysis. And the other event, which I showed with red curve, was not illuminated by removing the pulsar, this pulsar. And but we found that we concluded that the detection is not convincing. Also in the case of this red event, because we had a receiver configuration change around the same time, around the event time. And also the other pulsar, this PSRJ0437, blah, 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 reduce the detection statistics to so this pulsar was causing the high detection statistics. And this pulsar is famous for having high red noise, and this is among the pulsars most difficult to model. So we also removed this pulsar. So after removing two pulsars causing high detection statistics, we got this dashed line. And now you see that all the curves went below the expectation obtained from the simulation. So basically, with this result, we concluded that we didn't detect gravitational wave. And sorry,
roughly 5 minutes left.
So, sorry, I couldn't.
So you have roughly 5 minutes left.
Okay, thank you. So this is another thing to show, just to confirm non-detection, that so we made histogram of detection statistics, and originally we got high detection statistics up to 35, but after removing two suspicious pulsars, then we got the consistent result with the simulation of non-detection, without induction of gravitational waves. And from this non-detection, we can place upper bound on gravitational wave amplitude. And here we show the sensitivity map, that the sensitivity of pulsar timing array depends on the direction of gravitational wave, because pulsars are typically in the galactic disk, so they are kind of clustered if you look at in the sky map. And we found that the pulsar timing array is sensitive to the direction which is perpendicular to the direction of pulsars. So basically opposite to the pulsars of directions. And the sensitivity also depends on the width, we assume. So we find this tendency that for larger gravitational wave duration, we get the better constraint on gravitational wave amplitude. And using this upper bound on gravitational wave amplitude, we can also put constraint on cosmic string parameters. And as I showed, gravitational wave amplitude depends on the tension, G mu, and also distance to the source. And the distance to the average minimum distance to the cosmic string loop can be calculated by modeling distribution of loops. And as there are other talks about it, there are several models to describe distribution of loops. But we took one of the model which we have to assume initial loop size, and this we show the constraint on tension depends on the initial loop size we assume. And although we got different curves for different initial loop size, one common tendency is that we got the best constraint for longer duration of gravitational wave events. And using this long duration event, this is a summary of the cosmic constraints on cosmic string parameters. So vertical axis is initial loop size, and sorry, horizontal axis is initial loop size and vertical axis is the cosmic string tension. And this work put constraint on this orange region. Unfortunately, the constraint is very weak compared to other cosmological observations. For example, CMB put upper bound on G mu like 10 to minus 7. And also stochastic search in pulsar timing array put much stronger constraint. But one thing I would like to emphasize is that this is independent constraint compared to other cosmological proofs. And also in future, if we can if we can improve the sensitivity of pulsar timing array, then we can enhance the parameter space. So for example, here, this blue curves plotted assuming sensitivity of SKA, and you see that it can go beyond the sensitivity of current stochastic background. And if we assume clustering of loops inside our galaxy, we can even enhance the sensitivity. If there is more loops inside our galaxy, of course, we can expect this kind of individual burst more often, and the sensitivity is get enhanced. And of course, as many people mentioned, there was implication from nanograph 12.5 year data. So if that implication is because of gravitational wave from cosmic string, then it should go along the edge of this gray region, and that this parameter region can be proved by burst search by SKA. So this could be also interesting possibility. So here is the summary. So we searched for a signal of cosmic string gravitational wave burst using pulsar timing array data, and we provide that constraint on cosmic string parameters due to the no detection of gravitational waves. And it turned out that the constraint is weaker than the other types of cosmological observations, but again, it's an independent test of cosmic string. And in future, with SKA, we can expect better sensitivity in this burst search. So that's all. Thank you.
Okay, thank you very much, Professor Yanagi, for this very nice talk. Are there any questions? Please unmute and ask. I don't see any raised hand. Okay, if not, we're running a bit late. Let's thank Professor Yanagi again. Maybe we can have some questions during the discussion session. Thank you very much for the very nice talk. Yeah, so let's move on to the last talk of the session, which will be by Professor Yanagi. Professor Chui, can you just share your screen?
Hi, can you hear me?
I can hear you, but I
yeah,
cannot see your screen.
hold on. Let me see. Okay. Share screen.
Yes, now I can see your screen. Can you just
Okay, let me do the full screen here. Can you see the full screen here?
Yes,
Can you see the movie? Okay.
Yes, okay. Thank you very much. Yes.
Okay, great. Hold on, let me just. Oh, by the way, you can resume the recording. It stopped.
Yeah, I don't know how it stopped, but maybe maybe Anish can try something.
Oh, okay. I restarted. Yeah.
All right.
I heard that you requested not to.
Oh, I update it later.
Oh, okay. Okay.
Yeah.
All right.
Okay.
Good. Right.
Okay. All right. You can see the mouse moving too, right? On the screen.
No, I cannot see it.
You cannot see the mouse moving? Hold on.
No, can you move it a bit more?
Can you see the pointer moving?
No, I cannot see. Maybe somebody else can confirm.
Hold on.
No, we don't see
it. Some people can see it?
No, I cannot see it
either.
either.
You cannot. Hold on. Let me.
I think it's in the settings of Keynote.
Yeah, I did the testing. It said that the pointer, show pointer when mouse are trapped using this. It should be okay. Hold on. Let me see if I can do this again.
Maybe you can try again.
Yeah, let me see.
Can you put your pointer in this, maybe in this second slide? Yeah, can you move your pointer now?
Yeah, can you see it?
It's stuck at some point. That's what I see.
Yeah, same here.
I don't see it. I don't see it is moving.
Huh. Strange. Yeah, I tested on my end. Okay. Well, maybe we should just move on. It's not that essential. Okay. So I want to first thank the organizers for organizing this timely workshop and for inviting me to give this talk. So my talk will be based on a series of recent work with Marek Levitsky, David Morrissey, James Wells, my student Chapeng Chang, and also my UCR colleagues Barry Barish and Simeon Bird. So in the earlier talks in this session, we have seen that cosmic strings are well-motivated source for gravitational waves. For the general basic specs, I will refer to the earlier talks in this session. So in my talk, I will focus on telling you some other interesting new physics that can be imprinted in gravity wave signal from cosmic strings, including a couple examples of probing a very early universe and the connection to Axon physics. I will also briefly touch on the topic of how to distinguish stochastic background from cosmic strings or other cosmological sources versus their astrophysical counterpart, in particular by using the frequency domain information with the midband experiment. So we'll probably also hear more about this, the last topic in my collaborator Barry Barish keynote talk on Friday. Okay, so first topic, cosmic archaeology. So over the past decades, our understanding of cosmology has gone...
Excuse me, I don't think we see your slides changing. We are on slide 2 now.
I'm in slide 2. Yes. I'm also in slide 2.
Hold on.
I'm going to say that.
Strange. Do you see, what slide do you see now?
Slide 2.
Same.
Oh, it says sharing is paused. Okay, let me change this. Resume sharing. Sorry. I think I need to stop and redo this probably. Sorry about this technical problem here. Share screen. Can you see it now?
Yes, I see the slide 3 outline of the stock. That slide.
Can you see I move slides now?
No, I'm still in slide 3, outline of this talk. Slide.
Oh. You keep telling me this sharing is paused.
I'm still in slide 3. Maybe you can just
this
walk
is
up to and just remove the panels, and then you can do it instead.
I'm sorry. Screen sharing.
Yeah, maybe just remove the panels here and then.
Yeah, this way maybe. Yeah, maybe I have to go with this.
Also, can you try to remove the left panel? Maybe in view, I think you can do it. Go to view.
View, okay. Slide only.
No, click on the view, and I think there will be some. Yes, slide only. Yes.
Yeah, is it good now?
Yes, can you change to the next slide? Just let me just check.
Can you see me changing?
Yes, slide 4, slide 5. Yes.
Oh, okay.
Yes.
Can you see the mouse moving now?
Yes, I can see the mouse. Yes.
Okay.
See
okay.
Yes.
I don't know why the full screen share.
Yeah, let's just do it with this.
Okay. Thank you. Yeah, sorry about this problem. Okay. Yeah. So in the past decades, our understanding about cosmology has gone a long way. However, the earliest time where we have actual data to probe is the BBN time. And our best precision measurement tool so far, the CMB light, was emitted much later. Now, what happened before the BBN, the first second? For this, we do have a standard cosmology theory, but before the BBN era, those are all assumptions that are yet need to be tested. Well, there are many unknowns.
Yeah, can you go to next slide? Slide 5.
Yeah, I'm trying to do the next slide. Okay, good. Yeah, you see the next one. Yeah, sorry. Yeah, so the pre-BBN era, also called the Premature Dark Age, is a big gap in our understanding about the early universe. And this gap can be amplified if you look at if we plot the expansion history on the log scale temperature or expansion parameter. So this white region is the big gap. So in particular, in our paradigm, the universe is radiation dominated with standard model content from T equality all the way back to the end of inflation. But this is really an up to 20 ordered magnitudes of both assumption or extrapolation on the temperature scale. Is this really true? So now let's come back to this slide. So apparently it is desirable if we could have a direct way to probe this pre-BBN era, which includes inflation and also the long epoch of post-inflationary thermal history. And recently there have been studies that this non-standard thermal history could have a significant impact on dark matter physics. Now the good news is that we discovered gravitational waves. Because gravitational waves are very weakly interacting, so in principle, they can penetrate this BBN barrier and bring us information from a very early stage of the universe. So now the question is, how can we use this gravitational wave for this purpose in practice? So in my talk, I will show you that the gravity wave signals from cosmic strings provide a powerful tool to serve this purpose, to access this otherwise inaccessible era in the cosmic history. So in the earlier talks, we have learned that oscillating string loops would emit gravitational waves. And over the time, they would accumulate and form a relic stochastic background. The key thing is that for this source, there's a continuous emission throughout a long epoch of history. And consequently, the gravity wave spectrum span over a wide frequency range. So this continuous emission and the wide frequency spectrum is the key for us to do cosmic archaeology. So for completeness, I'm just flashing through some essential steps of calculating the stochastic background using this summation of oscillation modes method. The key thing for you to take note on is this final slide when we put everything together. As you can see, omega GW, the gravity wave density, can be parameterized in this way. The important thing is that the expansion parameter A as a function of the emission time T tilde appear in this expression. So this tells us that the cosmic expansion history or the Hubble rate in the very early universe is encoded in this prediction. Or put it another way, if we observe a certain pattern of the omega GW, we'll be able to extract information about the Hubble at in the early times. So next, we are going to first see the prediction from standard cosmology. You probably have seen this plot in some earlier talks. The solid black line is a prediction with the standard cosmology. One key feature in this spectrum is that towards a high frequency, we see a long, almost flat plateau corresponding to the emission during the radiation dominant era. Another thing that I'll elaborate more in the next slide is that we found that gravity waves within a given frequency band was dominantly contributed by loops formed at a certain time or temperature. So the cool thing is here is that as we look towards a higher frequency of this spectrum, we're essentially looking back in time to the earlier time in the universe. So in our work, we quantified this FT correspondence and found that this F and T has a linear dependence. Well, for the Nambu Goto, there's also mild dependence on G mu. This is in contrast to the global string case that I'll show you, where there's essentially no G mu dependence for this prediction. Now we want to see how practically useful this FT correspondence is by looking into the experimental sensitivity. And we found that with this method, it can enable us to probe the radiation history up to a temperature of up to 10 TeV. So another type of, so now we want to look into the possibility that there may be deviation from this standard paradigm, this radiation domination all along the way. The first example is to see if there's new phases or new equation states in the cosmic evolution. This type of non-standard cosmology is well motivated. For instance, early matter domination or kination. The presence of this type of new phases in the history can impact the gravity stochastic background spectrum through their impact on the Hubble expansion rate, as we have explained in the earlier slide. So essentially, different equation states give you different power law dependence of the rho or h on this expansion parameter A, which we parameterize by this factor n. Okay, now we want to do some exercises and look into some benchmark examples where assume that the radiation domination transits to early kination or early matter domination at 2 benchmark temperatures. So the rising line here, the prediction with kination, while the falling lines correspond to an early matter dominated era. So you can see that the deviation from the radiation flatness is quite dramatic. And the transition point in the frequency spectrum is exactly what we predict based on this FT relation that we derived earlier. Okay, so another type of new physics we can probe with this spectrum is the possibility of new degrees of freedom. New degrees of freedom are generically predicted in BSM theories, and possibly there could be hundreds of them. These degrees of freedom could be rather massive, so that they cannot be traced by CMB delta N effective or LHC. But through their gravitational effect, they contribute to the G star in the early universe as a radiation component. So the gravity wave spectrum could provide a way, again, through the impact on the Hubble expansion parameter. In this case, it's proportional to this G star. A particularly interesting exercise we did is to consider that new degrees of freedom arise around the weak scale. That can happen in some of the solutions to the hierarchy problem. Then consequently, as we see in the gravity wave spectrum, after a certain frequency, this plateau, the height of the plateau of the amplitude decline. The more significant when there's more G star that's appear at this scale. Okay, so another front of cosmic archaeology we can do with the gravity waves from cosmic string is this example where we consider the case that even if the cosmic strings were formed before or shortly after inflation, they are much diluted, but they can still yield observable signal today, particularly in forms of gravity wave bursts. So this study, the result is a kind of a counterintuitive example if we consider our standard law that inflation expected to bury all the relics that are present before it. So now how could this be even possible? We can understand this in a simple way by considering how the correlation length of the string network evolve. So during inflation, the correlation length gets exponentially expanded, and the strings are blown out of horizon from each other. But after inflation, the L scale with the expansion parameter A linearly, while the horizon size grows much faster with respect to A. So this gives us, shows us a prospect that the strings may grow back into horizon after inflation. And we denote this kind of a critical comeback time with this redshift Z tilde. Now we solve for the network evolution with Voss model with this particular initial conditions. Now what do we expect for the stochastic background, for the gravity wave signal? So first, for the stochastic background, we expect it to be suppressed, in particular at high frequency. We can understand this if you recall the FT correspondence. At earlier times, the network is diluted, things are out of horizon. So the signal is much suppressed, and later on they can come back and get stronger. Another interesting thing is that the gravity wave bursts in the standard case, as we have learned, is a subleading signal relative to the stochastic background. But in this case, because stochastic background is very much suppressed, this channel can actually be the leading signal. Okay, so our numerical results indeed support this expectation. As you can see, the stochastic background in this upper panel is suppressed. So the interesting thing is that because of this, the strong constraints on G mu based on, for instance, pulsar timing or LIGO observation could be alleviated. On the other hand, the burst signal, as shown in the lower panel, can be observable and also could be the leading channel if the string come back to horizon later. Furthermore, it's possible that the strings come back to horizon even much later after, say, the CMB time. Then the CMB bound on the G mu can also be alleviated. In that case, we would need to count on the very low redshift astrophysical signal to detect the cosmic strings. Okay, so the second part, now I want to talk about this interesting application for probing axion physics. Okay, so axion-like dark matter, axion-like particles is a leading alternative to WIMP dark matter paradigm as a dark matter candidate. And there has been a lot of interest in the recent years. But a relatively underdeveloped aspect of these studies is the implication of the ELP topological defects. So ELP cosmic strings domain walls are indispensable companion for the ELP particles if the peak breaks after inflation. So now our question is, could there be observable gravity wave signals from axion cosmic strings? This question had been overlooked for a long time, although it's potentially an important discovery channel. The reason it's overlooked is because by naive estimate, if we compare the power, the emission power of gravity waves and goldstone emission in this case, the goldstone obviously dominate and the gravity wave is very much suppressed. So one thing to note here is that a key difference between global string and the Nambu Goto string is that, or gauge string is that the string tension has this logarithmic divergence factor that we can denote with n that I'll quote when I talk about the simulation results shortly. However, even though the signal is suppressed, we have learned from, say, the Higgs discovery that rare decay mode could be the discovery mode. And on the other hand, you can say we can look for axion or goldstone signals, but the search strategy for the axion or goldstone signal is very much dependent on whether there's non-gravitational interaction with the standard model and what kind of interaction it is. On the other hand, the gravity wave signal is universal, while the detector sensitivities are improving. So the challenge is to do this study. First, there's a very limited literature compared to the Nambu Goto or gauge string case. But recently, there have been rapid development on the simulation front, although they are still not converging with many things to investigate. The key challenge is that for this case, the simulation has to cover hierarchical scales. Also, the things get more complex if we consider the scenario where there are domain walls that's formed. So our approach is we start with a simple case to consider the signal from pure global strings associated with the massless ghost zone, and then we'll step up to consider more complex case. We take a semi-analytical approach by using the Voss model, including the ghost zone emission, and calibrate the initial points with the simulation results that's available for low end or very early evolution time. Our study complements the efforts from the simulation work because for simulation, if you want to find the late time evolution that's most relevant to observation, you need to do a simple extrapolation of the low end data. But for us, we can take the low end data as input and predict the late time evolution by solving the evolution equation with the essential physics encoded. So this is our result with the standard cosmology. The key takeaway here is that we found that the signal is indeed detectable with upcoming gravitational wave experiment. And this finding was since then has been supported by some of the more recent simulation findings, although some details differ from our result. So now we can also compare.
You have roughly 5 minutes left. You have roughly 5 minutes left.
Oh yeah, okay, thanks. Yeah, so we can also compare with the Nambu Goto string case. So here you can see that in terms of the spectrum, the overall amplitude is smaller and the spectrum is redshifted. And at the higher frequency, instead of a flat plateau, it's a logarithmically declining tail. To explain this, we can trace back to the ghost zone emission dominance, and consequently, the loops are much short-lived, very short-lived, and also there's a log factor in the string tension. So for the FT correspondence, it's also very different from the Nambu Goto case. First, it's insensitive to eta, the symmetry breaking scale, or G mu. And the same F corresponds to a much earlier time or much higher temperature. Because of this, we can probe up to 10 to the 8 GeV with the spectrum in comparison with the 10 to the 4 GeV for the Nambu Goto case. Okay, in our recent study, we also consider how the non-standard cosmology or new particle species would modify the spectrum. Okay, so let me just briefly talk about the last topic on distinguishing the stochastic background from cosmic strings from astrophysical source. So one important thing to note here is that although it's very exciting for us to discuss the BSM opportunities with the discovery possibility opportunities with the gravity waves, but one thing we have to keep in mind is that if we want to claim discovery with confidence, we have to consider the astrophysical background, which can potentially confuse or contaminate our desired signal. So this type of signal indeed can originate from astrophysics, such as unresolved binary mergers. Possible solutions are being developed, for instance, to optimize the analysis in time domain, resolve the unresolved with more experiments. Our focus is to consider utilizing the information in the frequency domain. The key point here is that astro and the cosmo stochastic background generally have very different shape in the frequency spectrum. Binary mergers, for instance, goes like F to the 2/3 with a cutoff, while cosmic strings are rather flat at high frequency, and the phase spectrum has a split power law. So our work focused on the role of a midband experiment, which covered the frequency gap between the LIGO and LISA. And there have been many proposals. I've seen there are many collaborators or proposers of these experiments in this workshop. So our goal is to do a dedicated study, including explicit modeling of astro and cosmo sources, to see how a future midband experiment can complement LIGO and LISA to improve the sensitivity to the cosmological background and separate it from the astro source. So the larger perspective is we hope to help boost the science case for midband experiments from high energy or cosmology motivation. So I'm just to quickly show you the results based on our likelihood analysis. We consider both cosmic strings and phase transition, but for this talk, I just show you the cosmic string result. So first, if you consider the constraints, so the MOC data only have astrophysical sources, you can look at this 2D contour plots. This axis, y-axis here, these labels are for parameters for the astro sources, while G mu is the cosmic string parameter. So visually, so these red contours are with LIGO and LISA alone, while blue contours with the additional midband experiment. So visually, you can see that with the midband experiment, the parameter region is much more localized or a much better pinned down. So indeed, from numerical analysis, we find that with the midband experiment, we can improve the sensitivity to G mu up to an order of magnitude. The same thing we can find for if we consider discovery, where we do inject a cosmic string source to the MOC data. And again, with extra information from midband, the separation from astrophysical background is improved, and we can better pin down the parameters for the cosmic string, like the G mu parameter. Okay, so let me conclude. So hopefully in my talk, I've shown you that the stochastic background, gravitational wave background from the cosmic strings can be a powerful tool for constructing a timeline for the pre-BBN cosmic history. And the string, even if it's diluted by inflation, it may come back and provide observable signals such as gravity wave bursts. Furthermore, the gravity waves from global axion strings could be a smoking gun for the axion type of dark matter. And finally, a midband experiment could have a significant impact for improving the sensitivity to the stochastic background from cosmic strings or other cosmological sources, and better separate them from the astrophysical counterpart. Okay, thank you.
Okay, thank you very much, Stuart, for the very nice talk. Are there any questions? Please raise your hand and ask. Okay, I don't see any questions.
I actually have a question, a quick one.
Mm-hmm.
Yes, yeah, please.
Yeah, I'm wondering whether you can say a bit more about this proposal for the Tian-Go experiment, because I'm familiar with Tai-G and Tian-Quinn, but I'm not exactly sure what the proposal for Tian-Go actually is.
Yeah, the Tian-Go, it's proposed by a group of, I think it's a group in Caltech. So I think we first look at Tianjin, but then we found that the Tian-Go proposal, their sensitivity in the midband is better than Tianjin. So we chose to consider that. And also, we also consider BD-Saigo. These two are sort of comparable in terms of sensitivity, and it's not very long-term.
I see, okay. But what is the current stage of this proposal for Tian-Go? I mean,
the stage?
just the current stage, I mean,
yeah, they had a paper, I think, in 2019. We haven't seen much update, although it's mentioned in some talks. So yeah, it would be interesting to actually get a close update about that.
Has this been submitted to any funding agency?
I'm not sure, but I heard that they were trying to get some support from China. As you can see, the name is they have some Chinese collaborator, and this Tian-Go, Tianjin are both have Chinese origin. But I heard that there's still some uncertainty about what China would be inclined to fund. They have several proposals. I heard some rumors, but yeah.
Yeah, exactly. That's why I'm asking, because I'm wondering whether in the end it would even be realistic to have several proposals being realized. Yeah, so there's Tian-Go, but there's also the others. I think at some point, maybe if this has been submitted to some Chinese agencies, they would make a selection, right? And maybe only just fund a subset of these experiments.
Yep. Barry seems to suggest they might be inclining to find Tai-G, but I'm not sure what's the current status. I think it'd be nice. The Tian-Go seems to be a nice one.
Okay, thank you.
Okay, thank you. Are there other questions? If not, let's thank Professor Chewy again for the very nice talk. Hand it over to Anish.
So yeah, so we have like 5 minutes break and then we start with the panel discussion session. I request all the speakers, if possible, to stay in the panel discussion, and we will have a few more panelists as well. So we meet at 6:42 Central European Time. Thank you.